In this video, we'll learn how to add and subtract vectors and how to multiply them by scalars. Let's start with adding vectors. There are two techniques to add vectors, graphically and numerically. Let's start with the graphical technique. Follow these steps to add vectors graphically. Draw one of the vectors. Draw the next vector such that its tail is placed at the tip of the first one. If there are more vectors, then keep stringing them together tip to tail. The addition of all of the vectors is a vector that starts at the base of the very first vector and ends at the tip of the very last vector. Okay, let me demonstrate this technique with an example. We're given two vectors, FA and FB. Find FNet, which is the addition of FA and FB. Following the procedure, first draw one of the vectors. It doesn't matter which one you start with, so I'll start with FA. Then place FA such that the tail of FB touches the tip of FA. The addition of FA and FB then is this vector that starts at the base of the first vector, FA, and ends at the tip of the last vector, FB. Now let's do this addition numerically. Here's the same problem, but now we're given vectors FA and FB numerically. FA is 5 newtons, 53 degrees clockwise from the negative y-axis, and FB is 10 newtons, pointing in the positive x direction. And the coordinate scheme is given as well, with the positive y-axis pointing up and the positive x-axis pointing to the right. Vectors FA and FB are given to us in polar form, but here's a very important rule to know when adding and subtracting vectors. Vectors can only be added numerically in Cartesian form, and as we'll see, that's also true for subtraction. So we must convert these vectors to Cartesian form first. Okay, let's do that. Starting with FA, I'll make a right triangle out of it and show the given information. Doing the trig, we then get the x and y components. Notice I've signed the x and y components. This is critical and an easy thing to overlook, so be careful to always sign the vector components when you write them down. Now I'll write FB in Cartesian form. This one is easy because it only points in the positive x direction. So the y component is 0, and the x component is the full magnitude of the vector. Now that we have the vectors in xy form, we can add them. The technique is this. Find the x component of the answer by adding the x components of the individual vectors, and find the y component of the answer by adding the y components of the individual vectors. So we add these x components to get the x component of FNet, and add these y components to get the y component of FNet. So now we have FNet in Cartesian or component form. Let's compare it to the graphical result we found earlier. Isolating FNet and putting it on a coordinate grid, we could show +6 and -3 here, so it looks about right. Now we have one last thing to do in this example. We have FNet in Cartesian form, but we often need the final vector to be in polar form, so let's do that conversion. I've run out of room on this screen, so let me clear some of the work and move FNet up. We can find the magnitude of FNet with the Pythagorean theorem, which is 6.7 newtons, and we can find the angle clockwise from the positive x-axis with the inverse tangent, which comes out to be 26.6 degrees. We now can write FNet in polar form. So FNet equals 6.7 newtons, 26.6 degrees clockwise from the positive x-axis. The next thing I'd like to discuss is how we deal with the negative of a vector. As an example, let's find the negative of this velocity vector. If we do the trig, which I'll leave to you as an exercise, this vector would then have these x and y components. To get the negative of this vector numerically, we just multiply by -1. This can be done when the vector is in Cartesian or polar form. The result is this. Notice in polar form, all I've done is applied the negative to the magnitude, not the angle. In Cartesian form, I distributed the negative so it is applied to both of the components. If you drew this negative vector, it would look like this, which we can clearly see from the Cartesian components shown here. Maybe it's not so clear with the polar coordinates, so let's take a quick look at that. Here's the original vector on a coordinate grid. If we leave the angle unchanged and make the magnitude negative, that means the vector goes in the opposite direction, so back in this direction. And then this agrees with our previous findings using the -4 and +3 coordinates. Notice the graphical method of showing the negative of a vector has just been demonstrated here. Simply take the original vector and reverse its direction. By the way, we can rewrite this vector in polar coordinates with a positive magnitude and reference the angle differently like this, where in this example the magnitude is now +5, but the angle is clockwise from the negative x-axis rather than clockwise from the positive x-axis. And typically it's a little cleaner to use positive magnitudes and then write the angle accordingly. And now let's talk about subtracting vectors. The basic rule when subtracting vectors is to add the negative of the vector being subtracted. As before, we can do this graphically or numerically. So let's practice with this example. Given the displacement vectors a and b below, what is the result of a minus b? Let's do this numerically first. Based on the subtraction rule just stated, we want to add the negative of vector b. The vectors are already in Cartesian form, so we don't have to worry about converting them like we did in the original example. So a minus b is a plus the negative of b. So following the subtraction procedure we were just given, a minus b is a plus the negative of b. And then writing in the vector components, we get this. And so the x component is 7 minus 2, or 5, and the y component is -4 minus 2, or -6. So the final answer then is 5 minus 6 meters. Let's check this graphically. First, draw one of the vectors. I'll draw a first. Then I'll add the negative of b, which gives us this resultant vector, which if we put the vector on a coordinate grid, agrees with the numeric answer we just found. The last thing we need to cover regarding vector math is multiplication and division by a scalar. Any vector can be multiplied or divided by a scalar. Again, we'll do this graphically and algebraically. Here's an example to demonstrate both techniques. Given vector a below, find the result of 3 times a. Let's do this graphically first. Here's vector a. 3 times a will make the vector 3 times longer, but in the same direction like this. So that's all we had to do graphically. Numerically, 3 can be multiplied against the vector when it is in either form, Cartesian or polar. In Cartesian form, multiply each of the components by 3, which gives us final components of 9 and -12. Now let's do this multiplication when the original vector is in polar form. If you do the trig, vector a can be written in polar form this way: 5 meters, 53 degrees clockwise from the positive x-axis. To multiply vector a by 3 when it is in polar form, multiply the magnitude of the vector 5 meters by 3, which is 15 meters, and so the answer is 15 meters, 53 degrees clockwise from the positive x-axis. Notice that the angle is not affected, just the magnitude. Let's try another example. Given the same vector a that was used in the previous example, find -1/3 of a, which is really also a division problem. It's a divided by -3. Graphically, we make the magnitude of the vector 1/3 of the original length. And because we're multiplying by a negative, we also reverse the direction of the vector. So here's the original vector and -1/3 times that vector. Again, this can be done numerically in either Cartesian or polar forms. In Cartesian form, we multiply each component by -1/3, or divide it by -3. So the Cartesian components of the resultant vector come out to be -1 and +4/3. And then using the polar form of vector a again, we multiply the magnitude by -1/3, which gives us a resultant vector that is -5/3 meters, 53 degrees clockwise from the positive x-axis. As we discussed earlier, when the magnitude of the vector is negative, we can rewrite the vector with a positive magnitude and adjust the angle accordingly. Perhaps the easiest thing to do is to look at the picture that is drawn here and recognize that these angles are the same, so the vector can be written with a positive magnitude that is 53 degrees clockwise from the negative x-axis like this. Okay, so that's the end of the video on vector math. Be sure to also check out the worked out example on vector math that is posted on Moodle. And thanks for watching.